Okay. Hola a todos. Aunque sé hablar español, yo creo que voy a hablar en inglés porque tengo mis lecturas grabadas en inglés. ¿Y es un problema para alguien? ¿O está ok? Pero después, digamos, en el tiempo de breaks, vamos a hablar en español. Y probablemente durante los tutorials. Ok, voy a cambiar en inglés. Okay, hi everyone. So my name is Sergey Glazer. I'm from several places. So I'm from CERN. I'm also from the University of Florida. And I'm part of one of the big experiments of the Large Hadron Collider called the CMS experiment. Now, today we're going to talk about machine learning. And specifically, what we're going to cover are, by the way, how many of you already know what machine learning is? Nobody? Okay, good. Then we'll learn all that today. And we'll cover the theory, and also we'll go into the practical aspects of it. So, going back to the question I just asked, so what is machine learning, right? So it's a very simple thing. So in fact, it is a science of its own right now. It has a fancy name. What it really, really is about is algorithms, right? Not just any kind of algorithms. The type of algorithms that tend to get better at some particular thing. So you have a task, and these algorithms, they learn. They're almost like children. You have to teach them. They have to learn from data and their environment, and then they can go and do things on their own and eventually become adults and go vote and drive and all that good stuff. So machine learning algorithms are also the same way. You have to train them, and they have an ability to learn. And it's a class of algorithms. So if you have some kind of a task, and you give them some time to learn, they will do it. So what is a typical task that you can have? Right? So the task can be identifying if a particular picture is your best friend, or some unknown person, or a cat and a dog, or apple, or pear, or is this particle a Higgs boson, or some other particle that happens to look like it? Right? So it depends on your field. Now, what is the general idea? The general idea is you have some training set of data. You put your data in, right? It's a vector, right? Vector of inputs and outputs. So what's inputs? That's the stuff that goes in, right? Those are the ingredients. That's the data all around you that you can use to learn from. The outputs, now that's the things you're after. So if you're after classifying images, then then they belong to certain classes, right? So those classes of images they become the output, right? If what you're looking for that you want to learn is something continuous, maybe it's a function, maybe it's some parameter you want to estimate, and that's something you really care about. Maybe it's the temperature, maybe it's some other thing, or I don't know. You pick. Then your output is a continuous variable, right? So in this case, the output is y, and you also have a function space. So what that means is that you're trying to build a model, right? A model that's going to approximate that specific function, right? That output. That's going to take the input and give you an answer. So you're building a model. And there's certain classes of functions that are really good at this. And for that reason, that's not all the functions that could be, right? It's a subset of those functions. Yeah. And there is some constraint that makes them rather unique. But what you're doing is you're trying to learn a mapping between your inputs, right? You want to build a function that's going to give you the outputs. That make sense? Very good. Now, just to give you an idea, it's already the way sort of like de facto, state of the art in many things already. So for example, in computer science, when it comes to things like, as you already saw maybe earlier, some examples, for natural language processing, speech recognition, computer vision, big area. Self-driving cars. They use all these algorithms to figure out, oh, is that a pedestrian? Is that a truck? Or whatnot. Robot control. So you put these things also in cameras and robots, and you try to figure out also how for them to react based on the inputs that they see. And also, as you saw, there's also applications in medicine, things like that. Now, it's growing really fast. Why is it growing fast? This field has been around for a while, but it's been going through these spurts of many pushes, many revolutions, so-called. We're in the middle of one right now, but this is not the first one. Probably not the last one either. So, but right now, the reason it's growing is because the algorithms themselves are improving. And I'll tell you how much they've improved, even in a short time. And that's really why, you can't really argue with good results, right? So when these algorithms start to outperform humans in tasks, humans start to notice, right? And they say, well, maybe we should invest more in that. And the other reason is because you also have a lot more data, right? As you know, we are monitoring many things, right? We're putting satellites all over the place. We're putting sensors. We have cameras everywhere. We're tracking things from anything, daily lives, how much food we eat, how fast we drive, how everything, right? So now we have a lot more data. And now, because there is more data, we can study, look for patterns, and try to do better at specific tasks. But these algorithms are actually very data hungry. They like data. So the more data you have, the more you can actually learn from them, if it's a useful data. The other part is that because the software that you need to do these things in any other way is kind of complicated to do by hand. So what that means is that even though you have experts in all these fields that can go and do doctors are a perfect example of I guess, some learning algorithm, right? They learn, get their experience, they learn all sorts of things, and then you present them with some inputs, and they say, based on your symptoms, I think you are whatever it is, sickness you might have. And but basically, they're like an algorithm, right? Some kind of a decision algorithm, right? And sure, it takes time to get all that knowledge. Now, these algorithms can learn this stuff, and it's become a little too complicated to do all that by hand, right? And you can do it a lot faster and oftentimes a lot more accurately by doing it automatically. That's the idea. Now, what are some examples, right? So one example, right, is images. You probably have seen this. This comes from certain competitions which have been around for a while. But the idea is that you want to identify what object is there in an image. Yeah. So is this a child? Is this a person? Is this a dog? Is it a chair? If you're driving in a car and you want to see the scene all around you, that's sort of what the cars see. Right? They have these lidars and whatever else, and they're trying to analyze that to see if there's any obstacles, how the self-driving car should behave, so on. So you can also you can also apply it to analyzing handwritten digits, right? And what's amazing about this is that we humans make mistakes when we look at other people's handwriting. Why? Because everybody's handwriting is a little bit different. And even when it comes to writing simple things like numbers, right? You can see that there's then different ways that people write number 7. So these algorithms have also been quite successful in interpreting these digits. Sometimes even more successful, again, more successful than humans. So that's why it's also really interesting. Now, what I'm going to show you now is actually just more of a general idea how you can think about machine learning more of a mathematical sense, sort of on a high level, right? You have, we talked about this function space, right? These different function spaces that you have. They're not all kinds of functions you have. You have also specific constraints that you apply to these functions. And in the end, what this comes down to, it doesn't matter what method we're talking about. It doesn't matter if it's a decision tree, if it's a neural network, if it's whatever new method people come up with. In the end, they have something in common. And the common thing is that when they're learning, when these algorithms are learning, they're trying to optimize something, some cost function or some loss function. You want to make less errors. You want to make less mistakes, right? So you're building models that are trying to get better and make less frequent mistakes, right? And that means you're monitoring some kind of a loss function, right? You're trying to minimize the loss. That's the idea. Now, in mathematical terms, there's something called empirical risk. It's just a fancy way of saying that this function, right, of the inputs, the model that you built is going to have some adjustable parameters, some parameters that you can tune, or the algorithm is going to self-tune these parameters. You can learn them, right? And these are these weights W. And the idea is that these models, kind of like, they have parameters that can be adjusted, right? And you can end up with new functions of the same type, but they will adjust so that you minimize the specific risk. Now, in the end, the constraint itself, this L comes into here. The loss function is there, and it's a function of the output, and this function, which itself is a function of these weights, right? So all you're doing is minimizing risk, which in this context means minimizing your mistakes, right? That makes sense? Any questions so far? Okay, well, what does that mean? That really means that you can have a ton of different methods. And that's why it tells you there's something more fundamental than any specific method, because they're all unique and really different from each other, even though there's some connections between them. But all these methods, neural networks, boosted decision trees, they all may seem really, really different, but all they're doing inside of them, they're actually minimizing not just any kind of loss, but actually a very specific form of this loss function. It's a quadratic loss function. Does that mean that this is the answer? That that's how it will be forever? No. It could be there'll be other things that we haven't seen yet, okay, that work. It just empirically this seems to work really well. That doesn't mean there won't be any other ones, and the future will not change the specific statement. But the current methods actually minimize a function basically of this form, right? And what you're doing is you're comparing your output, and this model you try to get as close as possible to this output, and then you're basically looking at the square of that as the form of the loss. So what you're doing in the end, if you put in this loss inside of the same risk function, all you're doing is just putting this equation inside here. And that's your constraint, and that's where you're trying to minimize. The bottom line, all these methods try to minimize the loss, minimize the errors, minimize the so-called empirical risk. Okay? So what you should take away from this is it doesn't matter, okay, if it's, I don't know, support vector machine or genetic algorithm or a neural network. Underneath, there is something in common. And that's the common thing among them. Okay. Now, a little bit of history. I think actually it was really nice that there were already some talks earlier, so you have already some of these ideas maybe mentioned, introduced. So I don't have to do that again. But in this case, I think it's interesting to go through this because the field is not new at all. So the field itself was born, kind of like around World War II, even earlier, right? And but the first methods were really, you would say, invented in the 50s, so to speak. And then there was sort of like a growth period. People were very optimistic. They had no real computers at the time, right? They had things called computers, but you can imagine they would take up the whole room, have a whole bunch of vacuum tubes, but they didn't have that much either memory or computing power. So the methods themselves were really more theoretical, and they were very much limited by the computing power. But the moment the computing power has become sufficiently advanced, then you can all of a sudden start to try to see whether these methods actually work in practice. And over time, by the time we got to the 1990s, now you've got computers that are reasonable computing power, and new methods appeared that took advantage of these. So again, neural networks and et cetera showed up around that time, even though the ideas that came into them preceded them also by decades. But it only became practical around then to really tackle this in a big way. Now, what has happened since? Well, in the 2000s, early 2000s, really is when things have really kind of exploded in the applications, in the industries, and the academia. There were some problems, right? So there were some problems, and not problems, but more like challenges. Why these methods reached some sort of a saturation point, and it was really not clear where the future would go to. And then, as usually happens around this time when things plateau, new ideas come up. Problems get solved, and that was really when this sort of deep learning, we call deep learning revolution, started to happen. And the reason it's a revolution is because the improvements were so significant, right? And I'll tell you a little bit also where the improvements came from, because they didn't all come from one place. It was actually maybe 3 or 4 different places, 3 different ideas that came into this. But part of that is because there was also improvement in the computing, because between 1990 and today, there's actually a 1,000,000-fold improvement in computing on average. So you needed that as well. But there were also algorithmic improvements and sort of improvements in the learning. And they call it deeper learning. I'll tell you what that means, just a buzzword. Do you have a question? Yeah. Oh, a better loss function. Well, if I knew a better loss function, I think it would be already implemented, right? It would be already used. People have experimented with different loss functions. So far, loss functions of that form seem to work really well. Okay? But I'll give you an example of why I think that's not the end answer. And the reason I think so is if you know a little bit about the history, I'm going to jump ahead. So forgive me for doing that, but I'll do it now. And I'll give you a little foreshadow of what's to come. Since I'm talking about one of the reasons why these same algorithms have gotten really, really much, much better, one is that for the longest time, when somebody finds a solution, somebody finds an answer, like everybody else follows them. You build a track through the forest, people tend to go through that track, right? You kind of try to improve the road. And then a few of the people, stubborn ones normally, they kind of say, okay, you guys go this way, but I'm going to go and try and find maybe there's a better way to go. And sometimes they fail, sometimes they don't. And many times when people hit a roadblock, they just say, okay, that's the roadblock, let me go find some other way. There are others that are going to go and actually some of their photos you might have seen in the earlier talk, they were kind of considered giants now of this deep learning revolution. They weren't satisfied with the wall that was hit by others. They said, well, how do we get through this wall? And one of the reasons that the deep learning revolution actually occurred was because for the longest time, people thought that there was only one specific kind of function which is called an activation function, which is inside of neural networks. The people empirically found that worked. And that's why everybody and their mother was using exactly that form, because it worked, right? Nobody questioned that very much. But that function actually came with some problems, some undesired behavior that kind of led to the fact that you hit the wall in the first place. So it allowed these methods to work up to a certain point, but then the so-called vanishing gradient problem appeared that didn't allow you to get the full potential out of this method. So some more stubborn people said, well, why don't we try some other ideas? And they tried other ideas, and now actually, most of the functions that are used are of the other type. So in fact, finding something that works is not a guarantee that that's actually going to be the optimal thing. So you should always question. You should always question each assumption, and everything goes into each part of whatever it is you're doing. So people didn't question that for the longest time. And then they questioned it, and that led to good results. Which is why I'm telling you, the squared form of the loss function is what people have empirically found to work. Whether one should question that, you can kind of guess from my answer. Yeah. Okay, so I jumped a little bit ahead, but we'll come to that part. Don't worry. Don't worry if I mentioned things you don't really know about yet. So we'll cover some of that. Okay, so this is where we are today, right? And we're in the middle of one of such revolution. Now, let me give you just sort of an example of this. So this is a standard sort of competition. So these guys and girls who like to do computer vision, right? They said, well, why don't we actually establish a competition so we can monitor how well the whole field is doing, right? The best ideas of every year, so they come up with this competition. And you can see the winners of this competition were judged by something called the error rate, right? They would basically get a data set with, I don't know, some pictures and photographs, and these algorithms would have to figure out what is in them, what sort of classes and other. And what's interesting is that humans also make mistakes when looking at them, because some of these images were somewhat ambiguous. You can't figure out, is this a sandwich? Is it I don't know, a hamburger? Or is this a hot dog? Or I don't know, whatever. People still would make mistakes sometimes on this sort of things. But you can see that around 2010, the winner of this competition, the best algorithm in the world, at that time would be around here, about 28% error, which is quite a bit, quite a lot. And then you can see the errors, kind of like went a little bit lower the next time. And then around 2012, the first sort of deep learning algorithm entered the competition, right? And then what you see like, ooh, wow, half the error. That's actually a big deal, right? So you can guess what happened next year. Most of the entries were of the deep learning variety, right? So, and you can see that the winner over here was already starting to get down. Well, this is what happened the following year. You see the arrows keep going down and down and down. And this is a huge deal, because you go from an error which is around 30% to an error which is around now, let's say, 5 or 6%. That's a huge. That's not like a little change. It's not like, oh, I just got a little 10% better. That's on an order of magnitude decrease in the error. That's why it's a revolution, as opposed to just a little incremental thing. Now, I didn't really show you the end of this, right? But I can tell you, maybe as a little sort of fun thing to think about, humans are, I think they're about 5% error, something like that, 4.5%. Well, I can tell you that in the next subsequent years, these algorithms have surpassed humans in this. So now we're, all the way down at the bottom of this. So this should give you the idea of the amount of improvement that many different domains, not just this specific domain, have seen from the latest modern versions of these algorithms. Okay. Now, what that means is that all these blue guys also use machine learning too, just that not exactly of this type. Okay. Now, let's go back a little bit to the basics, right? Let's go back a little bit to some more fundamental things. So let's talk about classification theory, because one of the major sort of tasks in machine learning has to do with classifications, right? It's not the only one, but that's the classic one. The word classic is in classification, right? But the idea is that it's like categorization or classifications. When you have a bunch of classes, very, very well delineated classes, and the goal is to, given some input data, figure out what the outputs are. What class do they belong to? Yep. And there's a theory that comes with this, right? And the idea is that, you have, let's say, two classes. Let's simplify this, right? Something we call signal, something we want, one class, maybe background, something we don't want. We want to separate these two things, right? And you want to do as good job as possible in separating these classes. That's one of the sort of tasks. And what you end up doing is you end up building some kind of a model that's going to separate them as good as possible. So what you'll see usually in the end when you build your classifier, that's, let's say, a machine learning model that's going to do classification, what you'll see is that it's going to try and separate your two classes as much as possible. And there is some theorem, actually there's some nice statistics theorems I won't go into, but I think you can all find them. That tells you, what's the most optimal place, to put your decision boundary and say, okay, to the right, likely to be things of this class, to the left, likely of this class. However, there's always going to be errors, right? So there's errors of two kinds, alpha and beta. This is just classic, statistics. You guys should already have seen this. But the idea is that you're trying to minimize the error rate, which actually combines them, right? And but the caveat that I'm going to tell you about is that there are some problems, right, where these two things are unbalanced. Actually, medicine is one of those things. So it means that not every error you make has the same penalty. So let's say you're trying to classify images that maybe have, I don't know, you're trying to figure out if someone has cancer or not. That's a big deal, right? So obviously getting it right when you're right, obviously getting it wrong when you're right, and vice versa, has absolutely different implications, right? So oftentimes this is an unbalanced problem. Yeah. But generally, a machine learning algorithm is going to try to minimize that together. Okay. Now, the idea is this, right? Just like you saw that, you have some kind of a cost, right? So you have a cost of getting, when it's truly background, right? But you called it signal, or vice versa. That's the error of the first kind and the second kind. So again, it's a combined loss, right? It's the loss of this cost of misclassifying your background and the cost of misclassifying the signal, right? That's a fancy way of saying that. And there's a decision boundary. Remember, there are decisions to be made based on this, right? Why do we need these things, right? We're supposed to use them for something. So you make decisions based on that, right? So let's say if you were looking for the signal, right? And you wanted to isolate your signal and you don't really care that much about the background, then what that means is that, you're really after this region, right? So you could put a decision boundary over here and says, I want things to the right of it. Yeah. So what we do with the outcome or outputs of these machine learning algorithms is actually an entire science in itself, right? It's decision science. Yeah. But this helps you also to make, informed decisions and better decisions. But you need to be aware of the fact that even though these algorithms are learning, and they are sometimes, depending on what type of an algorithm, is it supervised learning or non-supervised learning, I'll explain to you what that means, or semi-supervised learning, in the end, right, it's up to us also to make that decision or maybe program that decision into the algorithm. So you have to be aware of what are the decisions that you're making also based on the algorithm. So something just to keep in mind as we're talking about this. And OK, so here you have a simple sort of boundary, simple one-dimensional thing. You say, OK, here, I'm going to make a decision somewhere there. Now, that means that anything to the right of it is something you're going to accept. To the left, you're going to reject. That make sense? Any questions so far? OK. Very good. Now, I know for a fact that they've done some good studies that said that it's hard to pay attention for more than 20 minutes, even though you may be very interested in this and whatnot. I know we had a long day. So I will go a little bit more, and then I'm going to stop. OK, we're going to take a little 5-minute break and do something else, and we'll come back and we'll continue. But let me just go a little bit further before we stop. OK. So this is classification in theory, right? This is all theory. Maybe what I'll do right now is tell you what these words mean when I say supervised, unsupervised, semi-supervised. Now, what does it mean supervised, right? We're supervising kids. Yeah, these guys are like kids, right? So we have to teach them. Now, how do you teach, right? In this particular case, supervised means when you're training the model, right? You also have some expert, the adult, or I don't know, nature, or whatever else. You have some expert, a doctor, or some way you know the truth that you can say, okay, here's the data, here's the outcome. I'm going to take that as my ground truth. Okay, the expert believes this to be the case. He analyzed the image of this cell and concluded that it is indeed cancerous. And this expert, after analyzing millions of such cases, and knowing the outcomes, he looked at the cell and said, no, this looks basically benign, right? So there is an expert who tells you what the answer is, okay? And then these algorithms learn from the data set, from this data set that already has the answer. So put in the inputs, here's the answer. Build the model, okay? That's called supervised learning. Then what you do is once you've learned the model, then you can go and apply it everywhere else where the expert didn't tell you the answer. So of course, it's a way to kind of build up an expert system and replace the expert, right? And say, I don't need you anymore. And now let's use this algorithm. Maybe sometimes they end up doing better than the experts themselves. But this is the supervised training part. Okay, you held its hand as you were learning. Now there are other ways of learning. So there's also semi-supervised or weakly supervised, where the role of the expert is a lot smaller. Okay, and you don't give all the answers that you could. There's also fully unsupervised learning, where you just have absolutely no expert implicitly put in during the training stage, and you just basically try and identify patterns within the data, and you try to learn from the data itself without imposing too much prior knowledge. So that's what I meant by that, right? And actually, all of this applies really everywhere. And but specifically, I can tell you that majority of the algorithms right now are supervised, the ones that are used. But there are also some unsupervised. And as was mentioned in the earlier talk, and I actually quite like that quote, that unsupervised learning is sort of the dark matter. Jan LeCun was actually at CERN recently for a seminar, and he was a former physicist, actually, with interest in physics. So I heard him say that, actually, a few times. And I can tell you that, indeed, it is kind of like the holy grail, so to speak, for many machine learning enthusiasts. Because supervised learning is sort of like, okay, it works, it's good. But the unsupervised is sort of like that, that mysterious, not hard to get to work kind of thing. And that's why it's also quite attractive. So anyway. I think I'm going to stop here for a little bit, and we can pick up on the practice part in a little bit. So let's take a 5-minute break. If you want to stretch out, you want to, I don't know, whatever you want. So we'll start in 5 minutes. Yeah. but we're not going to start there. We're going to start with another method, and I'll show you why in a little bit. So let's see. Is that good? Okay, thank you. Okay, so how do we construct these? Now, first, sort of the bird's eye view, right? What are we doing? Let's pretend we have two classes, right? F and G, or two types of densities, and we have training set of observations, right? We have some data. Right? We're going to do supervised learning. Forget about unsupervised learning for the moment. Forget about any of that stuff. Just remember, all we're doing now is going to do supervised learning first. So we have some inputs. We have some outputs. We have to build a model that connects it, right? So all we're going to do is we're going to take these observations. We're going to give it to a learning algorithm, whatever it is, neural network, decision tree, whatever you want. And then we're going to get outputs in response to the inputs, right? That's how it's going to behave when it's done. You've trained it. You give it inputs. It's going to give you the answers back. Okay? That's the idea. And then we're going to use a completely independent set of observations to evaluate how well we did. Because obviously, the place, you don't want to do that in the place where you've learned, because you kind of cheated, and that's kind of where you learned, right? So you're too optimistic. So we want to go to something totally independent. And we'll discuss also a little bit later what are these criteria and what are these sort of evaluations that you have to do to ensure that your evaluations are fair, and how do people do this, right? So we'll get to that. But the main idea, all we're doing is trying to separate two classes. Okay. Now, what that really means is we want to actually get the lowest probability of error on the cases that we haven't seen, right? That's the goal. That's what we're after. Yeah. And what we're going to do is we're going to basically do supervised learning, right? Labeled examples. We know them, so we're going to learn from them. Okay, now, if I wanted to actually give you all the algorithms, machine learning algorithms that exist, this would probably take 3 pages of this, but I kind of condensed some of that down. And here, kind of not necessarily in the order of complexion, but you have something like more linear type algorithms. Some of them are quite old and classic, but they're actually kind of, nobody uses them anymore, or they really shouldn't, because they just aren't powerful enough. But if you wanted to understand how things work, they may not be a bad place to start. Then you have things like kernel density estimation and a few others. But then down here in the second half is you're really getting to the algorithms that people really kind of like to use these days, right? So what are they? You have tree-type methods. There's different kinds. And you have decision trees, boosted decision trees, or other kinds. I'll explain to you what that even means. But in the end, they're basically tree-looking like algorithms, or ensembles of these algorithms, right? So you have things like random forest. Don't worry if you don't know these names. Well, I'll teach you what they are. And but then there is also other kinds of algorithms. So there is neural networks. All of you probably have heard something about it, right? And then we'll talk about them in depth a little bit later. And you also have deep neural networks, which is kind of like the lingo for this deep learning now, right? It comes from this deep depth. And then you have other things like support vector machines, genetic algorithms, and the list sort of goes on and on and on. But these are sort of the main types. Now what we're going to do is we're going to pick, we're going to pick 2 of them, basically, 2 of them, and go really in depth, right, for one of them. So, but just to give you an idea, so you have like a visual idea of what these things are doing, right? Let's say you have 2 kinds of balls, right? Red balls and blue balls, and you have some similar, let's say, 2-dimensional sort of pretend situation, right? So the idea is that you're trying to separate these 2 classes. Yeah? You can do it by eye sometimes, right? You can look at the whole thing and say, hey, what if I just draw a line through the middle? That's going to kind of separate, make sure most of the reds are over there, and most of the blues are on this side, right? So that's basically what this linear and Fisher discriminant does. It tries to find this boundary, which is a linear boundary, right? A line that's going to best separate your data. That's all it is. Okay? If you are doing something more like a quadratic, you can change the form of this and go to something. Oh, maybe I want to do something more fancy, right? It's a little more fancy. That's going to perform better. So you can do something quadratic, right? Now, this is very simplified. Why is it simplified? Because not all your data is 2-dimensional, right? Once the dimensions start to grow, the imagination of the problem starts to become a little complicated, right? That's why humans aren't necessarily as good at this as machines, because oftentimes you end up with, I don't know, 1,000-dimensional problems. Good luck imagining that, right, in your head. But anyway, but this is the general idea. So then the next kind of algorithm that we'll focus on, I actually like it as an example, as sort of an introductory example, are called decision trees. Binary decision trees, because in this case, whenever you make decisions, you only have two directions, either the left or right. Right? So the things, like trees, branches, sometimes you can have 3 branches. In the binary case, it's only 2. That's why it's binary. But in the end, they are nice because we all have seen trees. We all kind of know how they look like, and it's an easy thing to visualize. Okay, so what is a decision tree? Okay, now let's slow down and let's actually drill down inside of what this thing is. So now, here's actually the easiest way to look at it is actually to look at a tree. So here's a tree right here. Now you can see there is first of all structure, right? Why is it a tree? Well, if you kind of invert this thing upside down, it looks like a tree, right? So in reality, the root of the tree is up top. The branches start going down, 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 and the leaves are at the very bottom, the so-called leaves, right? Now in this specific diagram, you see that there are these sort of boxes over here, right? And these are your variables, right? Your input variables, right? So you have something called humidity, wind, and outlook, right? Something that you can measure. Humidity you can measure. Outlook apparently can have. Actually, this is not a binary one because it has 3, right? Anybody notice that? But anyway, in this particular case, you can have an outlook that's sunny, overcast, or rainy, and the wind could be either strong or weak and high and normal. Just to tell you what this problem is, this is a classic problem called golf. All right? And it's basically, the funny thing is that I realize that people in different countries like to change the problem. So in some countries like Brazil, this problem turns into soccer, football, sorry. So anyway, it probably would have a similar thing in Mexico, I guess, because, I don't know. But I know people play golf here too, so it's okay. I'll keep that. But anyway, the point here was that this followed around a person, right? Some hypothetical person. And it looked at his past behavior, right, on certain days. And they kept track of something like, okay, was the weather sunny, whatever it was on that day, was the humidity high or normal, wind so and so. And then they looked and saw, did that person actually go and play golf or not? It doesn't have to be a real person, but anyway, that's the example, right? And the idea was to learn and build a model which is going to be able to predict, based on some new values of these variables or features, it's the same thing, of what this person is going to do, right? That makes sense? Okay. But you can actually represent that model as a decision tree. So this here is the outcome of the training algorithm. So this is already the end result. The end result is going to be a tree. So when you train a decision tree, in the end you're going to get a tree, and that tree is going to be capable of giving you an answer. So notice these things in square, they're called decision nodes. Okay, here, that's why it's called a decision tree, because each node represents a decision, a binary decision. So let's say a new data point comes in, right? And the very first thing you're going to look at is the outlook. And if the weather is sunny, overcast, or rain, you're going to go in, you're going to make a decision, and then you're going to go either this way, or this way. And at some point, once you make these decisions, you're going to end up in the end in what is called the leaf, right? And the leaf is the actual outcome. So in this case, it's a binary thing, so it's a yes or a no. Play golf, don't play golf. Yes, no. So if some new data point comes in and the outcome is overcast, then this decision tree is going to say, yeah, go play, because every other time it was overcast, you played. Yeah, so that's basically what that did. Now, if it was rainy, it turns out it gets complicated, because now it turns out that sometime this person actually played golf when it was raining, depending on the wind. If the wind was okay, he went and played, right? If the wind was strong, then he said, forget it. Rain and wind, no golf, or whatever other sport. That's outdoors. Let's say the outlook was sunny. Well, here there was a different issue. The issue was humidity, right? And there, based on the humidity, if it was high, he didn't play. So this is pretty logical, right? Seems like this person does fairly logical things. But this is the sort of procedure, right? So you input the data and you look at the features, you look at the decision node. Based on the value of that variable, you make the decision, and then you proceed to the next node. That's how it works operationally, once you've done training, right? But what we're going to do is we're going to actually open up the algorithm itself and figure out how exactly did you obtain this tree. We didn't talk about that yet. Right now we just used about what it looks like and how do you use it. Before we do that, any question about the structure of the tree or how it would be used or sort of the idea of what it is? Or is that part pretty clear? Yeah? Okay. If you have any questions, by all means, stop me, interrupt me, and then we'll discuss it more. So, okay. Now how are these things built? It turns out they're built recursively, right? So that means that you take your parameter space, right, which is built from these from these variables, and then you start recursively partitioning it, right? You try to partition it, and you try to partition it in a way that starts to separate the two classes as much as possible, right? So the idea is that once you've made that decision here to go this way, now you've partitioned your data in some way, right? And then once you come here, you partition it even more, and eventually you're going to end up with more or less pure. I say more or less because it's not perfect, right? This thing is not meant to be perfect. There's going to be errors. But the idea is to arrive at parts of your parameter space that are as pure as possible. What does it mean pure? It means that the majority of the majority of the instances, right, that are contained inside that space belong to one class. Majority. Right? So what you're doing is you're trying to build, if you're a mathematician, right, or a statistician, then maybe that this multidimensional histogram will appeal to you, right? But this is the idea, is that you have things in multiple dimensions. You try to build these like buckets, right? You try to separate your parameter space and split it into different buckets. Now inside of those buckets, whatever is in them is going to be, you hope that what you arrive at, that whatever is inside of there is going to belong to one certain class. Okay? That's why they're multi-dimensional histograms. Now, you can even think about this if you're, this could be something like a doctor, right? Just change outlook by temperature. Here you can put, I don't know, blood pressure and, I don't know, some other symptom somewhere else. You can build a decision tree. So in fact, doctors, and I can tell you I have a few in my family, are really very much glorified decision trees, right? Very well trained, but still decision trees, right? So anyway, so the idea is that in the end, you end up with some answer, right? Some class. Okay. Any questions? Good. Now let's go and figure out what's actually happening, right, when you start to construct. Well, first of all, let's talk about, like, kind of, again, just quick recap, right? Each of these nodes, right, does a test. It's a test, right? Is humidity greater or less than something, high or normal? By the way, these don't have to be, words. These are discrete. These are discrete sort of attributes. So it's sunny, overcast. It could be something like temperature, which is a continuous, and in that case, it will be greater than some value or less than some value, right? So don't get the idea that these have to be discrete. They don't have to be discrete. Now, the nomenclature is, this is a decision node. These are branches, like branches of a tree. And these are leaves. Leaves are basically the classifier, right? So in the end, you get a bunch of leaves. And these leaves are what gives you the answers. So, and because it's not perfect, it's some probability that you have some specific class. Okay. Now, here, this y, this sort of output, the class, right, it's discretely valued, right? Now, keep in mind, it doesn't have to be discretely valued either. You could also be trying to predict a function, right, or approximate a function. But that's more of the regression problem we briefly mentioned. But let's forget about the regression problem for now and just focus on that. What we're doing is trying to classify things, distinguish two classes from each other. Now, typical instance would look something like this: humidity high, wind weak, outlook this, and you want to get an answer based out of it. So you feed it in the tree, we'll give you an answer, right? The question is, how do we arrive at the tree itself? Okay. Now, in the end, okay, this is still how it works. So let's continue. Now, how do we build the tree itself? Okay. The way it works And in fact, what I'll do, I'm actually going to draw on the board just for fun, just to give you a little bit more sort of a step-by-step idea how that works. But the idea is that you have, let's make it really simple. Like, let's pretend we only have two variables, 2 dimensions. So let's say, good. So here is variable A, and here is variable B, right? So all the data that we have is, something like A, B, and then here comes the class, right? And here there are some values, here there are some values, and then here there is maybe a class. And maybe in this case, let's make a class like little stars or circles, circles, stars, stars. So let's say this here is the training data. Okay? Now each of these is an independent value. I mean, this could be something like some number, 5, I don't know, 3, 7.2, whatever, 6.9, and so on, right? So each one of these represents a point on this 2-dimensional graph, right? So by the way, sorry, this is supposed to be straight, but actually let's make that straight. But I need, is there okay, whatever. Pretend this is straight. Okay, so let's say you had some stars over here, some star there, some star there, star there, there, maybe a circle here, a couple circles there. Something like that, right? And that corresponds to your input data. Now, remember, we're smart, so we said we're going to build an algorithm, but we're going to build the algorithm just out of the training data, right? That's all the algorithm sees is the training data. Thank you. I can make it straight now. Thanks. Okay. How's that? Okay. By the way, can everybody see? If anybody cannot, I can also switch over there. But if everybody's okay with this, fine. So okay. So you see that our input space looks something like, something like this, right? So some value for A, AI, BI, and here there is some class, Y, I, right? Now, when you're building a tree, right, what you're doing is you're going to try and subdivide this space, right? Now, because they're trees, because of the way the algorithms are designed, is the way you're going to partition the space is always going to be sort of rectangular or perpendicular. So we're not going to draw any fancy boundaries through this. We're just going to draw boundaries like that. Straight lines. Now, what you're going to do is you're going to, at very first, right, we want to arrive at our first sort of node, right, the first decision node. The very first decision is actually very crucial. How do you arrive at it? The way it works is you're going to take the whole space of each variable and you're going to subdivide that in some way. Make some divisions, okay? Equidistant. You're going to do the same thing over here. Okay? Now, what you're going to do next is you're going to scan along each of these variables. So you're going to forget this guy exists, right? And all you're going to do is based on this variable A, right? You're going to say, what if I make a boundary here, right? And I'm going to count, what's to the left, what's to the right? How well did I separate the two things? And you're going to give it some separation measure. We'll talk about what that measure is. But ultimately, all it does is count, how many are going to be on the right, how many to the right, what's the proportions within each of these buckets. So now you're going to have, something like this and something like that. So you're going to have two divisions, right, there and there. Or let's say, you did the same thing here, same things there. Let's say over here is a proposed decision boundary. Proposed doesn't mean it's taken. It's still proposed. And what you're going to do is you're going to say, okay, I have two, on the right I have 2 stars and, and 2 circles. On the left I have 4 stars and 3 circles. And you're going to compare, and that's going to have some kind of a value, right? Some kind of separation, right? And you can derive, there are some very well motivated metrics from information theory that actually they're they're actually based on entropy, the idea of entropy, complexity, that you can quantify how well you've done this separation. Okay? But all you're doing is scanning along and seeing what each proposed decision, how well it does, just based on this variable. Okay? That's the first thing. You scan along this guy. And then what you're doing is independently, or in parallel, the way it happens is actually in parallel, you do the same thing over here. You forget about A, and all you do is subdivide B, and you look at all the different proposed decisions. It could be here, it could be there, it could be there. And each of those is a proposed decision. It's a proposed split. Each of those has some gain, some information gain. And the gain means how well the two guys are separated within these two, as opposed to the original one that had no such separation. That's what you're comparing to, right? So now you have different possible splits. So what you do is you scan along this and you find the value of A, right, that maximizes the separation based only on A. And let's say it was here. Let's say A was something here. Let's say this is 4. I'm just making up a number. So what that means is A says, hey, cut on me, cut here. Make the decision over here, and you're going to do the best you could possibly do based on me only. Okay. B says, oh, but guess what? If you cut over here, let's say, I don't know, let's say here. Oh, you're going to separate really well. These guys are all alone here, and then this is a pretty good split. So this is, he says, based on the scans just along me, this is the best decision, independent of anyone else. So B says, B equals 5 or something is the best decision. And then you put them head to head against each other. And one of them is going to win. Okay? So either the B gets the better decision or the A gets the better decision. But in the end, only one wins. And let's say A won. That means that he got the first node. So that means A greater or equal to 4 and A less than 4 is actually that very first decision. Okay? But it was achieved in a competition, which is why these methods are pretty cool, because they're based on something that happens in, I guess, in nature. But the point is that in the end, this single decision that you saw, whatever it was, Outlook or whatever else, it means Outlook won in the very, very first node when you try to partition it. Okay? And then you repeat the process. So let's say A1. So now you actually draw this as a decision. So the very first decision was to split the space into 2 parts. And now that it's split into these 2 parts, right? So that's the node now. Now you have 2 subspaces, here and here. And that's why this algorithm is recursive, is because now you go ahead and you treat each of these spaces as now totally separate, don't talk to each other, and you repeat the process for each one of them. So what that means is over here is the next competition, and here is the next competition. And now what you're doing is subdividing just this part and this part, and again, you arrive at some decision. Let's say B1 this time, right? Because look, perfect. If you split along here, you've got wonderful separation between the stars and the circles. So great. So B equals 5. This is here. So B greater than 5, let's say less than 5. Here you can actually put class labels. And the class label is star. Oh, am I doing this right? Yeah. And circle. Right? Now you've reached your leaf because guess what? You cannot do any better now. Right? You stop. Because, well, in this case, you just totally perfectly separate them. But instead, there's also some stopping criteria. Like you've arrived where there's too few of them, or the separation you just cannot do anymore because if you separate it, you end up with getting less separation. So you see, now you've reached the leaf. A decision. Right? Prediction. And here is a little more complicated, right? So here you may have to go, a few more times. to get to a leaf. But in the end, what you're doing is partitioning the subspaces, until you get to things that are more pure. That's as pure as it gets in this case. That makes sense? Okay. Any questions? Okay. Now I'll just let you sink in a little bit, right? What do we do? All we did is we put these different variables, the input variables, right, head to head against each other. And what we did was we scanned along them, and we looked at possible ways to separate the two classes based on those variables. They competed against each other. Maybe at some point, this is actually very nice. This is, in computer science, this is an algorithm which is called a greedy algorithm. A greedy algorithm is an algorithm where it's sort of like life, because each decision affects the next, right? Because suppose B1 here, it would be a totally different tree, right? So, you know, there is an element of nonlinearity in a way, right? There's an element of competition and also kind of like each one affects it, which is why they're very nice structures. Now, to give you an idea, nobody uses single decision trees these days. But to understand more complicated algorithms based on decision trees, it pays to understand how these work. This is just one variant of a machine learning algorithm. Why? Because this is all done automatically, right? You don't go and look how many are here, how many are there. The algorithm kind of keeps track of that, right? And finds you these, scans along, finds the optimal variable. Now, optimal variables. But just remember that this is a competition. And this algorithm is really based on the competition. Okay, so that's it. It's pretty simple, right, if you think about it. But there are some subtleties that I haven't talked about yet, so I'll tell you in a moment. But what does it say here? You scan along each variable, propose a decision, and then you make some sort of a decision base that maximizes class separation. There's something here which I haven't said, right? How did we actually estimate this separation? I didn't tell you anything about that. I just told you some magic words that somewhere the algorithm figured that out, right? But let's actually figure out what that's from. Now, what are we after? Think about what the end goal is over here. The end goal is achieve the leaves, right, that are as pure as possible. That they're all kind of all of the same class. So you can look at something called the purity, which is all it is just simply the number of proportion of objects or whatever instances of one type over the total, right? So, for example, a signal leaf is going to have majority signal events. Background leaf is going to have majority background events. So, for example, this right here is clearly a star leaf, right? So star, let's call signal star, right? So that's a signal leaf. That's the background leaf, right? But you can also have, let's say originally in the data there might have been a star here, right? So this is still a signal leaf, right? Because it's majority of the instances in there are of that type. Yeah. Okay. Now, the goal is to do this, but the idea is that you want to increase purity. So every decision should make things that are more and more pure, right? And in the end, you stop when you just can't get any more pure, or you just run out of instances to divide. Now, what is this separation gain that we talked about, right? Now, here comes another point where there are more than one option, right? And people have actually tried many different things that work. But in the end, they're all sort of the same kind of type, variety, general shape, right? You can see it right here. Now, there's something called the Gini Index. And in the end, all of this, you can see that they're all kind of the same type, right? This P times probability, purity, whatever you want to call it, 1 minus P, right? Or P log P. And you may recognize from your physics class or some other place that you may be a freshman in physics or high school physics, that's actually the form of something called entropy, right? Remember entropy, the sort of measure of complexity, it exists also in information theory. It actually comes from information theory. And so what that means is that you can figure out, you can see the connection, right? You can see how many instances of one class versus the other. You can express that as entropy. And consequently, you can see whenever you have lower entropy, kind of like, second law of thermodynamics, and whatnot, right? It tells you actually, where the universe is going in terms of entropy, right? And order and disorder. It's the same idea, right? Here you want to go to lower entropy. You want to go to things that don't differ very much from each other, but they are as different as possible from the other class. That's why it's expressed that way. But remember that this function could have different shapes. But these are just the ones that people use because it works. Yeah? Okay. Any questions? Yeah? Break? I think it's not a bad place to take a break. So, okay.
Has something to do with the physical logic?
Ok. Damos unos 30 segundos más para quien todavía está llegando a su asiento. Ah, no. Ok, voy a otra vez cambiar al inglés. Ok, so. Okay, coming back to what we were doing. What we did was we looked inside one of the algorithms, right? We looked inside, we saw what a decision tree is, right? What is its structure? How does it work? And also how to build it, right? That's what we just covered, right? And what we established is that all you're doing is you're trying to separate the space, right? You're trying to isolate these different classes that you're trying to separate. You're trying to isolate them by subdividing the space, right? And you use some criteria to evaluate how well, these proposed decisions, these proposed boundaries, how well do they actually, how well do they subdivide the space, right? And we use different types of measures like cross entropy or Gini Index or whatnot to do it. So this is where we are now. So what are we going to do next? Now let's look at what a typical decision tree looks like. Actually, I drew one over here, right? But maybe you can't really see that very well. So this is, these are just some variable names, some variables, fancy names we use in particle physics. It doesn't matter. It can be anything you want. But in the end, it's going to look something like this. It's going to be decisions. Now, the important thing to know that these can be either categorical, meaning discrete, or continuous values. So, and in the end, you arrive at the classes, the leaves, and this background and signal, and that's what a typical tree looks like. So by looking at a tree, you can immediately see how you're subdividing the space, right? You can kind of figure it out. You can follow the tree along. The important thing to note, and that's something somebody asked me in the break, and I realized I didn't mention this because I explained to you how this worked only in 2 dimensions, or with 2 variables. Now, the nice thing about trees is it completely generalizes to arbitrary number of variables. What that means is that instead of having 2 of these, now you have, let's say, 20 of these, or 20,000 of these, or 20 million of these. But what's really happening is that they're all competing for the same goal. And you treat each of them independently whenever you're considering the splits. So in the end, only one wins the decision. Only one gets to be the winner. By the way, the same one could be then used later, because now you've subdivided that into only 2 pieces, but then you can go and subdivide that. So each decision, all bets are off, the slate is clean, they all compete again. Okay? But the point is that there's only one winner, but there could have been 10 competitors, right? And maybe tomorrow I'll talk about some of the issues resulting from this, because not every method is perfect. Each one has its weakness, each one has its strength. This one has a lot of strength, but also some weaknesses, and we'll discuss that also tomorrow. But it's a very good method to begin with, because you can intuitively see what's happening. And I would encourage you to never be afraid to actually open up the box and see why the method works and how, because then you'll understand what it's doing, and there's no mystery. Yeah, in this case, there's no mystery. Okay, now, one thing you can think about is that these trees can kind of become pretty big, right? They can grow a lot, right? So one of the things people have thought about doing is figuring out, can I end up with a smaller tree that still does as good? So what they do is something called pruning. And the idea is that you first build a really, really big tree. And then you actually do the reverse of what you were doing. You actually try to take your leaves, the resulting leaves, and combine them with each other and see whether you end up with something more. And the idea is to avoid something called overfitting. And I'll tell you what that is. Don't worry about that yet. But that is something that you need to worry about in general, and I'll explain what that is in a little bit. But that's something why pruning is a good idea. Because they're smaller, they're easy to interpret. Occam's razor comes in here. As long as they still perform relatively good to the really, really deep and complicated tree. Okay. Now, we've almost reached the end of the theoretical part for today. Actually, we have reached the end. And what we'll do afterwards is going to be a little more practical. So we're actually going to go and build our own first classifier. All right. So today, the goal of today, you're going to have your own first machine learning algorithm that's going to do something. And because we've learned about trees, then you can guess what kind of algorithm we're going to do today. But tomorrow and in the other days, we also will work with other algorithms. But today, we'll focus on the ones we've learned. So there is lots of, just to kind of summarize this part, there is many, many different methods. And that's actually really beautiful because there's something fundamental here that's not really connected to any individual method. Because you have n solutions, this means that the problem itself, there's many ways you can go about it. And the problem itself is not really tied, or the solutions don't have to be of a certain type. Right? And people have come up with many different ones. And the important message, as I told you before, is not to assume, right, that the way things are today, that's how it's going to be 5 years from now, 10 years from now, 20 years from now, etc. It's very possible that we may, as a field, find better algorithms. We already have been doing that. But the point is that there's no reason to think we won't also continue to do that. And the algorithms might be really different from anything you've seen so far, or anything that anyone has ever seen so far. So keep your mind open. And if you have an idea, try it. If you want to build your own algorithm, come up with some new algorithm, I don't know, maybe you can build it off of, I don't know, some fancy spiderweb inspiration, or some, I don't know, whatever idea. People have tons of different ideas. But maybe you'll come up with something new that works better than what other people have thought about. So keep that in mind. But all of these have something in common, right? And that this general approach that what you're trying to do is you're trying to minimize that risk. And there's certain forms of this function that you're trying to do, right? So that's something in common. And we discussed a few of them today. We're going to talk about some more advanced methods next time. But there's a lot of methods out there. Feel free to experiment. Don't take my word for that method X is better than method Y. There is no such thing. For different problem, a different method sometimes comes out on top. So there's no, even though you hear deep learning everywhere, there are problems where, for example, neural networks don't perform very well, and others do. So that's just a little takeaway message at this point. OK, so we're done with the theoretical part, so to speak. Now, what we're going to do next is we're going to actually do something practical. And for this, I'm going to switch this to something else. Now, let's see. How do I do that? Let's get out of that. And let's see here. Full screen. OK. So, OK, here comes, I guess, the actual tutorial. OK, so what are we going to do? Right? We're going to build our first classifier. If you've built already a classifier, it's not your first. I'm sorry. But for those of you whose it's first, it'll be hopefully a nice experience. So today, what we're going to do is we're going to build a tree-based classifier. So we covered decision trees. We're going to build a tree. And later on, in the other days, that we still have quite a bit of time. So don't worry. Don't worry if you want to learn about other things. We'll do those as well. So, OK, now. What are we going to use? Actually, it's not something we're going to actually use today, but since you've heard about it today, I'll throw it out there too. We will use that on Friday. On Friday, we're going to use Jupyter Notebooks. Now, what are these things? Now, I think somebody today, I think it was Gabrielle, gave a really nice introduction to Jupyter. Right? I don't have to do that again. But the point is that it's a really cool thing if you want to do interactive things. So basically, like you can have code, notes, you can work out of there. You don't have to have anything. You just need to have a browser. So that's really all that's required of you is to have a browser for what we're going to do. Now, today we're going to use something called SWAN. That stands for Service for Web-Based Analysis. That's something that's developed at CERN, that was developed at CERN recently. That's not to say there are not other things we could have used, and there are, and I'll tell you about them on other days. So you don't have to think it's the only thing out there. And besides, it's somewhat experimental, and sometimes it works, sometimes it doesn't work, and whatever. But there are other things you can use. But the nice thing about this service is that it gives you the back end for running these Jupyter Notebooks, right? And it's basically a service, on-demand service. And today, by the way, today, what we're going to do is we're going to use a very, very fancy terminal. So that's all we're going to do. We're not going to run, even though the SWAN is really meant to be used for running Jupyter Notebooks. We won't do that today. Today we're just going to do something more basic. I will show you a very classic machine learning tool that's specific for decision trees and tree-based methods that is super intuitive, no bells and whistles. So we're going to work with a classic, like a Chevy, like one of those classic cars. Sure, we have more modern cars now, but if you want to understand how cars work, you don't have to, do that. So we'll work with a classic today. Okay, so how do you log in? Now, by the way, I think there's more people here than we originally planned. So that introduces a slight complication because we only prepared a certain number of accounts. So what I will suggest, today it will not be a problem. We'll see how I'll solve this question for Friday, where it may be a problem, where I would like each of you to have just a single login. But today what we'll do, because it's a terminal and it's not a problem, I think if multiple people use the same account, what we'll do is you guys can actually split into little teams. Maybe you can work two. So since you're sitting desk of two, maybe you guys can pair up. So this way we'll reduce the number. And that means maybe you can use both computers, or you can just use one and look at the other if that's okay. Maybe that's a solution. But the idea is this. So what you want to do is you want to log into one of the servers. Here is the link. Let me explain to you what these X's and Y's are. So there's bunch of servers, 1, 2, 3, 4. So basically you want to go swan 001 or swan 002. If one of them doesn't work or feels overloaded, you can switch to another and whatever. Just randomly pick between them, so so not everybody's on the same one. It's gonna make it a little faster. Then there is a link here. Oh wait, I realize you don't have the thing. So how about this? At the end, okay, I'm gonna add the slides for today, and I'm gonna also add a link here, which is going to ask you to register. So this way we know you are the one who was logging into that machine, and then this is for security purposes. So later, we don't have to do this right now, but at the end of the day, since you'll be using that for all 3 days, if everybody could actually fill out, there is a Google form to keep track of logins. Now, the usernames are here. That's stat.lr, and then the next part, you just put some number between 10 and 40. But here's the thing, right? I think I'm just going to go and assign numbers so that people don't pick the same one. Yeah, so I'm just going to give you guys numbers between 10 and 40 today. And the password is the same thing, except the number that you have to reduce by 1. Yeah. And yeah, so let's do that. So how about? Okay, so how about 10, 11, so 10, 11, 12, 13, 14, 15, 16, 17 in the back, 18, 19, 20, 21, 22, 23, 24, 25 in the very back, 26, 27, 28, 29, 30, 31, and we're going to run out. 32, 33, 34, 35, 36, 37, 38, 39, 40 in the very back. 1, 1, 2, 3, 4, 5, 6, and 7. Okay. And so try to log in. That's your very first task. Oh, and I'm going to do it with you.
So for the password, which is the name you use,
Yeah. And then the number. Yeah, the number, but subtract 1. Yeah. Doesn't work? All right, let's see. Now, if some of you tried it and it doesn't work, that should not be surprising. Because I did forget to add something in here, and I actually did it on purpose. I just forgot to tell you. There's also an @ symbol. Security. So, sorry? So stat.lr @ and then the number -1. Yeah, really tricky. Yeah. Has anyone succeeded to log in? Yes? Good. Okay, so we'll wait for everybody to do it. And in fact, what I'm going to do is do it as well. So wait. I am messing up. Okay. Sorry for whoever has number 31. That's the one I'm going to use. So you just follow along with me. But you can also use it. Don't worry. But we won't. So you should see something like this. Wait. That's not going to work. How about there? So, so here you have some options, right? Did everybody see this? Okay. Now what you want to do right now is there's different software stacks. We're going to play with an experimental version. It's stat_lr at arroba, and then the number that I gave you, but -1. Yeah. So you have to do some math, right? It would be kind of boring if you didn't have to do some math. So here, what we'll do is you basically choose, you click here, and then choose development bleeding edge. It says might be unstable, but we're living on the edge, right? So let's do that. And then you click start my session. And then this beautiful bird is starting to ruffle its feathers and create the environment for it. So.
Start my session. So I use this.
Yep. Yep.
What's the button?
Stat_lr, at. No, sorry. So stat_lr at, and then 27. So it's 28 minus 1. So just get rid of this.
-1. Yes.
Okay. Anybody else has problems logging in?
Only we need the configuration. Environment is like the web or default?
No. You have to go here and choose the development bleeding edge on the bottom. Yeah.
Maybe mistake.
Yeah, it's okay. And then click start here. Excuse me. Yeah. Yeah. Click this, and then pick development bleeding edge. No, this one. Yeah. Okay. And then start my session. Okay. Yeah.
I'm the 10.
You're the 10.
It's at 9, but this not working.
Try 0, 9.
Okay.
I think it might be like that. Let's try. Yep. So if you're between 1 and 10, there's a 0. So if you're 10, you're 0, 9. If you're, I'm sure that everyone here has discovered that. Okay.
We're good.
You're good? Is everybody logged in? Good. Did you pick development bleeding edge? Good. All right. So we're ready to live on the edge. Okay. So what we're going to do today is going to be super, super easy, so to speak. Now, here you'll be able to do things with Jupyter, and we'll do that on Friday. That's not something we're going to do today. Today, we're going to use this very fancy button on the top. Do you see this button that's like a greater and an underscore? That's going to open a new terminal. Yeah, basically a console. So, let's see. Who is number 31? Okay, we're going to have to synchronize because we're the same number. So what you do affects what I do. So we'll have to, and what I do affects what you do. So maybe for now, just watch. And then after you can do what I'm showing. I can show you, yeah. So anyway. I'm actually going to start over. Quiet. Do Firefox. It's 1001. That's it. So did everybody succeed with the terminal? Did you get a terminal? Okay, great. Well, you're ahead of me because I had to quit this thing. So, okay. There it is. Yeah. Okay, so for those of you that are familiar with terminals, and we're going to use very, very basic commands, so don't worry, we're not going to do anything fancy. But what I'm going to do is I'm going to go back here. Wait. I'm going to go back over here. Okay, so we're done with this. So what do we do so far? We opened up a terminal, right? Now, the next part is you need to check out the actual tutorial. That's going to include stuff for today, stuff for the other days. Don't worry that there's going to be a bunch of stuff in it. We're only going to focus on one part of it. So what you have to do is you have to type this command into the terminal. So git clone, and then you give it this address. And I'm going to do it with you too. So git clone. Actually, I might have already done that, so I may already have it here. But go ahead, just type it out. Git clone, and then wait, you need to see it, right? So here, I already did it, so I don't have to do it, but you guys can do it. Yeah. How many of you have used Git before? Okay, a few, but you don't have to know how it works for this to work. Question? And hit enter when you're done. Yeah. Lowercase.
Yeah.
Stat lr 12. Okay, and here you want stat lr at arroba. Arroba, and then 11. Okay. Okay, you see it's doing something, right? It's getting the code. Okay, try 1, 0, 0, something else. Like 1 or 2 or 4. Okay, in the end it should tell you that you know, you've gotten 100% everything and you're done. Yeah? Did everybody get? Huh? Sorry? If you have a problem, raise your hand. No, no necesitas instalar nada. You need to work in the terminal, not your own terminal, inside of this. You need to go click this. Yeah. No problem. Yeah. What's the problem? Means you already have it. Here. Okay. Any problem? Is everybody good? Problem? Well, you're with me. You already have it. You don't have to do anything.
Send me here.
Whoa. Oh, you're in the local host. Did you?
Yeah, but this is a notebook.
Yeah. Don't do it in yours. Do it in this one.
Yeah. But open this one. Direct me here.
How about, because we have the same username right now?
Okay.
Just follow me.
Okay.
And then we'll fix that later.
Okay.
Okay. Okay. So, what do we do next? Git clone. You forgot the colon. After HTTPS, you have a colon. Yep. Okay. I'm assuming everybody got it. So let's go back here. So if you look at what you have here, if you do like list the contents, right? You can do ls to list the contents. I think I'm going to increase the font so you can see this better. Okay, that's better, right? So ls will show you. There's some other stuff. Ignore the other stuff. It's from other things. What you want is you want a folder called tutorial_unam. So to go to that folder, you go cd, change directory, and then you can tutorial, and then you can do an underscore, just tab, and then you can go inside there. Okay? We'll continue when everyone's there. Does anybody still need more time? No? Okay. So now let's look inside. Do another ls. And you can see there's a bunch of stuff here. Today you're not going to need anything except for the directory called C50. Okay? So what we'll do is, you'll need the other stuff later. But for now, ignore all that. So we're going to go cd, another change directory, and then you want to go C50. Okay. So now we're inside C50. And you can see that here you have, actually, is everybody there inside C50? Anyone need help? No? Okay. So that means I'm just going to clear so it looks nicer for you. Now we're inside of C50, and you can see there are some files. Okay. Now, before continuing, let me come back here. Okay. Now, what is C50? Anybody heard of it before? I wouldn't be surprised if you didn't, but some of you did. Great. C50 is a classic. Okay, that's that Chevy I was telling you about. Okay, it's a program. Initially, it was called ID3 algorithm, which then was called C4.5. The modern version of it is called C50. It was actually written by this guy named J.R. Quinlan, who was one of the fathers of the decision tree algorithm. So he has a fantastic book, by the way, this one right here called C4.5, where he describes more than you'll ever need to know about decision trees, and he's fantastic in explaining them. So if you want to understand the big concepts of machine learning, not necessarily tied to decision trees, but in the context of decision trees, that would be a really good book to read. It's fantastic. But anyway, this book comes with a program, and that's the program. Now this thing has decision trees and other decision tree type algorithms, like decision rules. I'll tell you what those are. And also boosting, which is something we'll cover tomorrow. So that's what you have right now is the C50. And today, we're going to do a couple different examples. Right? So what we're going to start with is actually the example of playing golf, the one we talked about earlier. So let's switch over to our terminal. And let's look at what you have. You have some data file, something called breast cancer. Ignore that for the moment. We'll look at that in a little bit. I think it could be interesting. Right? But then there's also, you see there is this few files called golf, right? Golf something. Now let's open them up and look at what they are. So the first one we should look at is the file called golf.names. That's like a configuration file, right? It's like where you tell the algorithm what are the things called. Okay. So what do you see? You see the very first line has two things: play, don't play. Anybody care to guess what that is? It's the class, right? That's the sort of like the expert labels. Then you have one by one the different variables. So outlook can be either sunny, overcast, or rainy, separated by commas. Temperature, it says continuous. What does that mean? It means it's a number, some number. Windy is a binary thing, so true, false. That's it. Pretty simple, right? Pretty easy configuration file. So that's all the algorithm needs to know. What are the classes, what are the variables, and their types. That's it. Now let's look at the data. So to do that, let's open golf.data. Okay, well, looks like this. You have, each line represents a day, right? And here you have, in the order you've listed in the configuration file, the values for, for the outlook. It could be sunny, overcast. So it's like, the first attribute is the outlook. Then you either have the temperature or humidity. I forgot which one's first, but anyway, they're continuous. And then false or true, that's the wind, right? Wind, no wind. And the last one, by default, is always the class variable, right? Play, don't play. So apparently that person that we are going to study That's what they did, right? So that's exactly the data. And now what we're going to do next is we're going to build a classifier model that's going to try and learn what happened that we can use to predict any sort of future potential outcomes. So how do we do this? We can use the executable here is called C50. You can see it. So if you do it ./C50, then you're going to call the the program that's gonna build you the tree, C50. And all you need to do is you need to give it the name of the configuration file. Now, remember that all of them start with the same name, golf.names, golf.something. So all you have to do is give it that name, golf. So there, like that. And you can hit enter. Ooh, something just happened. Let's see what actually happened here. Well, let's scroll up and see what happened. Well, the first few lines is like, oh yeah, I'm C50, right now, okay, somewhere there's this time. And then it says this: I've read 14 cases. Remember, there were 14 lines of stuff with 4 attributes from this file. Nothing fancy so far. And then look over here, this part is the actual decision tree. Well, you have to first learn how to read it, but it's not complicated. This tree, you should read left to right, as opposed to the ones we drew top to bottom. This is left to right. So the way you look at it is the first decision is basically the leftmost variable here. So you see, Outlook is the very first, so it means Outlook is the first one. So then it says if Outlook is overcast, outcome played. Right? That's what that means. If Outlook is sunny, now the decision is, now you have to go to the next decision. And that's, you see, you have ... Then comes the decision that subdivides that space more. So if the Outlook is sunny, depending on the humidity, if the humidity is less than 75, you play. If it's greater than 75, you don't play. Remember that decision tree we looked at? That's basically what it is. And then it says if the outlook is rain, depending on the wind, if there is wind, you don't play. If there is no wind, you play. Right? Can everybody read the tree? Now you know how? Excellent. Now, anybody care to guess what these numbers are? Good, correct. You're both absolutely correct. These numbers represent, remember this is the training data. In the training data, they represent the number of instances that fall into that bucket, right? That is in the leaf. Leaf is the proper name. That fall into that leaf. And you see it's only one class, so it actually perfectly separated them out. So this tree managed to perfectly divide all the data. Doesn't always happen, by the way. But this is a simple enough one that it works like that. So that's the tree. Well, is that it? Should we continue? Yeah. Let's see what else it has. Well, then it says evaluation on training data. Let's see if we can understand what that means. Now, what that says is in these 14 cases, right, it says there are no errors. Well, we just saw that, right? It perfectly classified all of them in these bins, buckets or leaves. So on the training data, the ones we've learned from, no mistakes. Now, this right here is called the confusion matrix. How many of you have heard that term before? Okay, let's discuss what that is. That right here tells you how well you're doing and where your errors are. Yeah? So what that means is you have 2 columns and 2 rows. The columns are A and B, A and B. In this case, each one corresponds to the class. So in this case, class A is play, class B is don't play. Here it says, what did the decision tree classify things as? Right? So 9 times out of 14, it classified them as play. 5 times it classified them as don't play. And based on the true knowledge, right, there are no mistakes. Mistakes would appear on the diagonal. What that means is if anything appeared here, it means it was really really play, but you called it not play. Remember when we talked about mistakes of two types? They would be right here. One of them would be when you took one class and called it the other, and vice versa. Yeah. Does everybody understand the confusion matrix? Or is it confusing? Yeah? Okay. But this is an important thing to know, an important thing to pay attention to, because it shows you where your errors are. Okay. No errors so far. So far, so good. Okay. And then some more information about how frequently you've used your attributes. Yep. Now, for this example, unfortunately, there's no actual testing data that we can test provided, right? So we don't know what that person actually did and wanted to find out what they did in the future. So for that reason, let's go to the next example, where we actually have some of that data. So you'll see that inside of this folder, by the way, if you want to look at the tree itself, it's also stored here. Now, notice there's another example here called breast cancer. So let's open up that file and see what that's about. So let's open up breastcancer.names. Okay. So there's some citation request. It tells you where the data come from. This is actual real data. This is actually real data from somewhere, from Wisconsin. And what it covers is there are different, keep going. There's some relevant information, whatever. It tells you how many instances are inside this data. There's 699 of these. There are 10 attributes plus the class attribute, right? So there are 10 variables. This data set is basically based on some information. They wanted to test whether, or be able to predict whether, build a classifier that's going to try and separate cases where a patient either had breast cancer or not. So benign or benign means no cancer, or malign, which means there is cancer. So pretty serious business. But it tells you what are the different, there are different attributes. It tells you what the different are. If you're a doctor, if you're doing some sort of medical analysis, these might actually mean something to you. But for now, let's just sort of treat them as some kind of explanatory data. Uniformity of cell size or bare nuclei, whatever those things are. Let's just assume they're variables that have some useful information. There's also some missing values, meaning you don't always have everything. And then here is the real part. This is the actual, that's the actual code. Everything else is like a comment. This is the actual configuration file. Okay? What that means is the first one, does anybody remember what the first line was for? The first line were the class names. Remember, play, don't play? 2 and 4 are the two class names. Okay? One of them means benign, the other one means malign, right? So 2 and 4 are the class names. Then you can see all the different variables. By the way, very good idea. The very first one, it says ignore. All that is just some ID to identify the patient. Obviously, you don't really want to use that, right? So that's ignored. Everything else is a continuous variable. That's it. That's all you need to do this. So next, let's look at what the actual data file looks like. Breastcancer.data. Okay, looks something like that. 699 lines or whatever it is of the first attribute is some ID number, which is going to be ignored. And then the rest are just some values for those variables. Cell size, bare nuclei, whatever else. The last one, 4 and 2, those are the class names in their own definition. One means have cancer, the other one doesn't. So it means that over time, they actually followed these people and figured out that they had cancer or not. Okay, that's what I think that means. Okay, so far so good. Let's build another tree. Okay, let's do it. Well, I'll let you do it if you remember how. But anyway, it's pretty easy. It's just, you run the executable, in this case, ./C50. And now instead of golf, you give it breast cancer. Now what I'm going to do is instead of putting it like on the terminal, I'm going to save it in a file so we can then look at it later. right? So I'm going to call it something like breast cancer dot, I don't know. I don't want to call it fun. So let's call it decision tree. Done. Pretty fast, right? Pretty fast looking classifier. Now let's open it and see what happened. Okay. Now you all should be pros by now, since we already went through one of these. So what does it say? It says it read 500 cases. By the way, you remember it said there were 699 in total? So what that means is we're going to use 500 of them to learn, and then we're going to use the rest to evaluate how well we did. That's the idea. So in this case, it read 500 cases from this breast cancer.data file. And then out here, you actually can see the tree, right? So the tree looks like this. It's still pretty reasonably not too complicated tree. So can everybody read the tree? Okay, so the very first attribute is this uniformity of cell shape. And then it says, depending on its value, if it's more than 3 or less than 3, that's the first decision, right? And then you continue and continue and continue. If the uniformity is less than or equal to 3, but blend chromatin is also less than or equal to 3, then you end up with some class 2. That's the first leaf that we encounter. If it's not, then you keep dividing until you reach another leaf, right? Now, notice, no longer is this a single number sometimes, right? What does that mean? Again, like before, what that means is that in that leaf, right, there were some mistakes, that it's not completely pure. So out of 310 instances inside that leaf, 3 were of the wrong class. Still pretty good, right? But not perfect anymore. You should not expect perfection, by the way, in the sense. So there should be errors too. So, okay. So then you have something like this, 97.1, 56.5 sometimes. Okay. Does everybody understand the tree? Or is there any question about the tree, meaning of the tree? No? Okay. All right, then let's continue. So now it says, now let's look at how well it does on the training data. It says evaluation on training data on these 500 cases. Now, not surprisingly, the error is non-zero. Out of 500 times, 9 of them were wrong. Still pretty good, but that's what it says on the training data. So 1.8% of the cases were misclassified, right? The next thing you can do is look at the confusion matrix to see, what is the distribution of these errors. So you can see that the diagonal term, so here the times where it was supposed to be A and you called it A, or 2 or whatever it is, class 2, is 322 times. 169 times it was really class 4 and you called it class 4, you were correct. So these are, the 491 cases you got right. And here are the 9 cases that you got wrong. 3 of them were, well, you misclassified, class 4, you called it 2. 6 times you did the opposite. Make sense? Excellent. And then it gives you some information about how often each was used in the tree. It's just some heuristic. Don't worry about that too much. Okay, now we're getting to the interesting part, and that's the evaluation on the test data. Remember, the test data, the algorithm has never seen. Doesn't know anything about it. So this is actually going to be a kind of a fair thing to find out how well it does there. What you can see already, since I already scrolled down here, is that of the 199 cases which were in the test file, it made 11 mistakes. So higher than the training. Of course, that makes sense, right? Because you've trained in one place, you're doing really well there. The real question is, how well does your algorithm perform where you did not train it, where you did, where you haven't shown it this information? That's more fair. So, and that tells you that, now your percentage is higher. Your error percentage is around 5.5%. for this single tree. Okay? Now, you should always kind of expect that, right? You shouldn't, in the sense where you learn, you should never quote the performance of your algorithm on your training data, right? That's never going to be a fair assessment of how well you're doing. You really should use something else. So we'll cover how to evaluate that in kind of like a modern way in the next, tomorrow, I think. We'll do that. But for now, this should suffice to understand the idea, right? Everybody have any questions? Yep. Oh, okay, very, very easy. I think in this case they just arbitrarily, randomly chose, 200 of them to be tested. But you can actually set that yourself. In all these tools, they allow you to do it. Either pick a random choice or 50, whatever. You can actually set the way you want to do it. So there's no like, rule for this case. In this case, it just all it did was you only have 2 sets. Nowadays, we do some more fancy things because you don't always have that much data that you can go and partition it in so many ways. So there's more fancy ways of doing it, and we'll talk about that next time. But for now, I just want to give you the idea that this is sort of a real-life situation where you've trained it, your performance seemed really great, but then in reality, you should tone down your expectations. But that's still really good. That's still actually a pretty good performance overall. Yeah. Uh-huh. Quite different? As in like extremely different?
Yeah. I have 1.8%.
Oh, but that's
errors.
the training data.
Okay.
Remember, we are looking at the test data now.
Ah, sorry.
Right? So the training data, we have the same. Right? Yeah? No, try again. I don't know. I'm not really sure. Code something else. I don't know, code something else. I'm not sure actually why you're getting this. Let me see. It works. Oh, I don't know how to do dash F. Okay, we can look a little bit later, but yeah. Yeah.
In this case, how the error decreases with the number of samples?
How does the error decrease with the number of samples? Okay, there is a question. And the question is, how does the error decrease with the number of samples, right? Now, that is a question that's not very easy to answer because in this particular case, you don't know that. If you give it less data, most likely you will not build such a good classifier also. And you may have some other problems that have to do with overfitting and whatnot that I haven't actually mentioned. But in any case, in general, you want to have sufficient data that you can learn from and build the algorithm. At some point, with decision trees, it actually doesn't really matter very much. At some point, you're going to saturate, and it's not going to get any better no matter how much data you keep adding. Because the point is you need to actually add something more useful, right? Now, that happens to be something of a weakness of the decision tree algorithms, something where actually some of the algorithms have a little bit more of advantage. And we'll talk about that tomorrow on Friday. But I think what I'm going to do is I'm not going to stop here. I'll tell you about one more thing since we have literally 1 minute. Or maybe not. Maybe I'll just stop right here, and then we'll pick up tomorrow. So, and I'll give you a little bit of time to ask any questions about anything today. So, yeah. Okay. Well, if you haven't built your classifier, now you have. Now you have your own one. It's not a complicated one. Don't get any wrong ideas. You can apply these. You can apply C50 on any problem that you have. You can do it. You can always do it. It's quick. It's easy. And you'll get pretty good performance out of it pretty quickly. Will that get you to the state of the art? Probably not. It's going to be maybe a little bit worse because it's a single tree, right? Well, what we'll talk about tomorrow is going to tell you how to get a little bit more performance and get a little bit closer to what the state-of-the-art algorithms would get on the same data. But this is a very good starting point. And you can see without too many bells and whistles, you can go and get something you can use already. So, okay, I think we'll stop here. And if you have any questions, feel free to ask me. I'll still be here for a little bit. And then we'll resume tomorrow.